Hello, everybody, and welcome back to the stream. I am Junchan, and today we are working on the NBody simulation. Um, hmm. I realized that yesterday I said I would change the schedule, and I'm realizing that, I'm realizing that I'm going to be shifting things around. That's what I'm realizing. So let's do that, because I've been actually doing a little bit of preparation for working on the NBody simulation problem. So basically, I'm going to cut down a little bit on my streaming schedule. I've been streaming 6 days out of 7 for now, maybe 6 or 7 weeks. And so I'm going to stream instead 3 days on Tuesday, Thursday, and Saturday, and looks like de facto our schedule is going to be this, because yesterday we did work on pure script, and then I announced a new schedule. So I think it kind of makes sense to alternate, and so now we are working with Haskell. And also, I've been trying to at least get us in the same place that we were before. Plus, today is the day where, let's see, did I even write this down? I didn't write this down here, maybe at the top. Right, switch to Ubuntu if we don't fix it by the end of the 10th stream. So this is the 10th stream, the beginning of the 10th stream. And so, this is not necessarily a super hard and fast rule, but I think we can, make it happen. So, not that I have anything against Ubuntu, on the contrary. But, I'm stubborn, and I've been learning some stuff. It's not... learning, I prefer learning more about Haskell and Accelerate and body simulation. But still, this is the we could say the ground we walk on, or at least several of us walk on. So it's not bad to have a pathway to build things properly. It might come in handy someday, because lots of people are on Windows. Actually, estimation of operating systems for end users. Yeah. Android 54%. Wow, that's crazy, isn't it? And iOS or Mac, and then Windows. I suppose. Yeah, even web clients and desktop. Desktop is still 76% Windows. So, yeah. So, I care about 76% of the desktop user population. So where were we last time? Well, we for the past 2 streams, we've shifted to an approach that is grounded in the way that the GHC team actually builds for Windows, and they have this recommendation. And following that actually went much better than any of the pathways that we've tried before. I didn't go with Stack. How did I do this? We installed directly, and we've been careful to run the Minji W64 executable. That's one of the things that we were having trouble. We were actually on a different environment before. Then we bootstrapped, did our instructions to build GHC, but because GHC needs to be bootstrapped from an existing GHC, they have instructions on how to install GHC and Cabal. So I followed these instructions. Last time I actually did an update Cabal, and I did so now. So everything's in the proper path and accessible here. So Cabal version should be 3.2.3.20, and GHC version is now 8.8.4. I think I downloaded 8.8.3 before. I updated that. Now it's 8.8.4, which is the latest 8.8 version. And then when running Cabal, now what is the current problem is the some weirdness with the way that paths are written in the CUDA library. So this problem didn't exist in the previous environment, now that I think about it. I wonder how or why. And also, it makes me wonder about some of the stuff that we did in the previous streams, where we had to put the NVMM on the path. Otherwise, we wouldn't have access to. We have this error message, and it fooled us for a while. But now I think it should be good. Except that right now our path is actually the default path, so we don't have any of the libraries in, and I don't think that's connected to the problem, because now we have like this really strange path. But it's not impossible that it's connected. So let's go back, because I think I deleted some of that path, those path entries. I did, and so let's add those to the path. And check, and it looks good. So let's skip our build. And like in the previous streams, while things build, if it gives us a little bit of time, we'll be checking out the actual Accelerate NBody code. Some of the interesting stuff that we found out last time was that the Barnes-Hut approximation algorithm for the NBody problem wasn't actually implemented in Accelerate examples. It's only using the n square ON square method, what they call the naive algorithms. So that opens up a possibility for us to implement it and contribute this, and that would be quite a nice contribution to make. And what else? Well, yeah, we did find also that there was the algorithm was implemented for DPH, data parallel Haskell, which is that it comes from the time where Haskell JC itself had a data parallel implementation. But that's been removed, and so that would be a completely different tangent there to follow. Let me see. I'm making sure that I'm actually connected with the chat, which I wasn't. And now I am. Okay. Oh, except it's not number 9, it's number 10. Yeah, the title of the stream was wonky. Okay. So we might go back to looking at how things were implemented in data parallel Haskell. And there's also a further stretch goal, I would say, which is to use one of the forks from a very recent paper that implements a particular subclass of data parallel algorithm compilation for Accelerate. And it seems like, at least for maybe part of the algorithm, the quicksort to build the octrees, it might be interesting to test out that branch. So those would be further, this would be great things to finally get to as we solve, and if we solve, our build issues. So let's see whether what I did changed anything. It doesn't look like it did. It seems to be trying to build Accelerate now rather than CUDA. It did a few things for CUDA, but but not all the things. And let's see how CPU usage is pretty well used. It looks like. Let's see. Yeah, we've got 3 GHC processes running and doing some compilation right now. So that's good. So let's well, maybe before we leave it be, let's take another look at what these error messages were, the ones with the path, because I think we found some GitHub issue that related to exactly that problem, and it didn't seem to have a clear-cut resolution, but still I think it makes sense to go and refresh our memory with what this said. So let's see. That's not exactly it. Unique style path. It's similar, very similar. The error messages don't end up being the same though, but it's at least related, maybe not similar. I think this was the closest one, and that was, yeah, that's right, and that was filed with Haskell IDE engine, and it was triggered by while using stack or create process. That's actually not the problem, but this is the problem right there. Same issue because stack was installed on the C program files. Moving stack to cbin stack was not enough, however. Had to uninstall and install the whole Haskell platform to see Haskell, blah. Before reinstalling the Haskell platform and stack base, install failed with Cabal, failed to build, blah, blah, blah. Failure occurred during the final install step. The exception was die verbatim library deals, C program doesn't exist or isn't a directory. And I think that's exactly what we have. Library dears, C program file doesn't exist or isn't a directory. So that's exactly what we had. However, this user suggests that after moving stack and the whole of Haskell into a proper path, then the error went away. It doesn't seem exactly like, I mean, so this suggests that it's related to the path of the build tools. The path before we modified it had no extraneous path, no path with with spaces or anything. So including the path that we're in. So the question becomes, where did this build then find these this problematic path? And then the natural answer would be, well, in the CUDA library. Even though those paths don't show up right here. And it's also worth noting that it seems like it's actually kind of compiling until the end, but it's afterwards when, which is still apparently part of the CUDA 0.10.2 build, but it's after compilation. So linking probably, yeah, failure occurred during the final install step. Same error message here. Cabal is in a path GHC PKG. Don't know what that is. But if you remember last time when we checked out... Oh, what happened with my code? Okay, it went all the way there. When we checked out what was in this new style folder, which might disappear from under us, and I think it was in the CUDA folder. Yeah, it's going to do this, so that's not really practical. Boy. And let's try and see whether we can solve this. VS Code, folders, close, while building. Collapse. Prevent from expanding, disable empty folder. Okay, nobody seems to be reporting this. This is strange. Ah, okay, so we bumped into the same problem. It seems like it completed a few more, but yeah, we have the same issue. So let's go check it out now that it's finished building. In CUDA build, where was this? Right, it was in place conf. And we have one for JHC883 and one for JHC884, and then also one for NVM, apparently. This seemed fine to me. So it's really something about how CUDA does this that's the problem. Although... Ah, right. Oh, this Haskell platform link is still here. So, whereas we uninstalled it, so that might actually be a remainder, and that might still be in the Windows environment variables, and I don't know why it would be picked up by MSys, but Windows environment variables, I think it's in the system. Right-click the computer icon, right? How do we do this these days? Windows 10. Go into settings and click on system. Yeah, so that's right. Settings. System, about, unless I click about and select system info at the bottom. Okay, now at the bottom. Now new windows that come up, select environment variables. Where is this? Advanced system settings, I bet you. Yeah, that's here. Oh yeah, I did miss that one. Okay. Let's see. CUDA path, NVM home, blah. Path. Don't see Haskell platform here. Maybe here. No. I wonder where this is picked up. Quite strange. So not in the environments then. It's not in the source code, right? Create 10.2. It's in the build info. Build info seems to somehow pick it up. So first of all, I think we can actually overwrite this. So that would be a way, but then the question is, how do you even generate it like that in the first place? I don't think this is an issue. We looked into this before, didn't we? But maybe not as much in detail. The build info, GitHub build info, reads user provided build info, otherwise lost CUDA build info dot generated. Yeah, that's cool, but how do you generate it? Oh, wow, that's a lot plain. Generate and store. Find CUDA install path. Oh, could it be? Oopsie, I'll do that. Find CUDA. Try to locate CUDA installations by checking in order. Yeah, that's all good, but this really doesn't explain all of this craziness. How about I delete it? Can I ask to build only CUDA? Is that possible? Looks like it's possible, but looks like it's unhappy about not having that file anymore, which is fine, except I would think that you just generate it. Okay, so let's just do get build, see whether that leads to the same problem. It does look different. Okay, no, same error. Default. You're not telling me it's in the repo. No, it's not. How do you why doesn't it generate it? It must be something about this, the state of the build. Maybe because this new style is there. Probably is the case. So let's just remove this new style here. And let's see if we can, actually let's see if we can just build CUDA like this. Doesn't look like it, but let's do the same thing. Right here. Oh, come on. Why? Oh, what? There's some GHC. There's still some GHC active, actually. So when I quit this build, it didn't clean up all the GHC.exe. Oh boy. Okay. I'll quit them manually, and let's go check this out. So this doesn't have, it does have the setup stuff. So let's just remove that whole thing. And see what's up. Yeah, it starts by building setup.exe. And it's happy not to have the generated file at this point. Okay, so that might help. Oh, okay. So no, let's okay, let's I don't know. Can I even quit that GC job? Okay, I think I finally did. That's also pretty weird and not satisfying, but that's the way it will be for now. Let's also remove the 883 folder. We don't need that. And clearly I haven't killed all of the GHCs around. Okay. And so yeah, what's setup config here? You don't want to tell me that. And the so the generated file does go there, and it indeed is still looking for the platform, Haskell platform. So let's see, maybe there is some code for Haskell platform in there. Platform. Maybe it's a setup.exe, setup.hs specificity. Let's see if there's anything about Haskell platform in there. Haskell platform, I mean, apart from the... There isn't, right? So where do you get this from? Okay, well, I suppose it's in this, there is a database, right? There is a local package database somewhere that I think is used by setup.hs. That comes from maybe package description or something. DB, yeah, this program DB, I think. So how do we see that and manipulate that? Setup.hs program DB, something like that. Uses package database. Creating a binary. Run Haskell setup.hs configure. So I wonder what Cabal does by default. Is this written somewhere here? Setup. Nothing clear here. I think it's probably coming from the environment because Haskell platform 865 is exactly what we had installed. So it must be querying some Windows related database, and we just need to find where it gets this stuff. Let's see. How about if we do, well, set might be a bit too much. How about env? Do we have Haskell platform in there somewhere? Nope. Doesn't seem we do. I'm double checking because for some reason I don't trust the search. Yeah, okay. Not there. Could be chocolatey. It's not in the path, so I mean, it could be something strange going on with the environment behind our back that we don't know about. It's completely possible, but users package database. Let's see if there's something there. Register and register. Installation path. Let's double check that we don't have this path anymore, or it could be that I suppose no, it's not there. Not there anymore, but still appearing here. So I mean, I think the other option, if we want to be somewhat maybe more efficient, is to just remove this nonsense and ask to build again. User provided build info will be used. So that's correct. And I don't see any more crazy nonsense. I'm not sure why it would, how it would find this path. This stuff is from Stack. I don't think it's used in the regular Cabal build. Oh. Really? Those are defaults. Well, sort of, right? Like really strange defaults. Huh. Okay, what's happening here? Okay, still some nonsense there because of libraries. So will all this be fixed if we add a prefix? Now, how do we specify a different prefix, but maybe in the Cabal file? Could we do that? Or does it just not make sense? Let's see, Cabal project prefix configure. Oh, 3.5. Wow. Global configuration file for Cabal. Yeah. How about that? What does it look like? You don't have a VS Code available from here. I think this worked in Alacrity, so let's open Alacrity for this kind of stuff. Code. It didn't. How about open Explorer? Yep. Well, not really. It didn't open in the right spot. So where would it be on Windows? Users, Cabal config. No, it doesn't exist. It doesn't. It looks like. But yeah, that's home June, and I think we want C users June, but that doesn't exist either. Okay. So do we want to do this? Possibly. What? Oh boy. Okay. This happened to us before. And this is what I did. Okay. Copy pasting is such a complex technology. Really? Oh boy. I suppose my laziness is punished. Oh, okay, so it was in another place. Of course it was, and actually I think I remember now faintly bumping into the exact same thing on stream. Yeah, of course, those paths don't work here. Yeah. Oh, that's where it is. That's where those things are. Oh yeah, I'm glad I insisted with this. Okay, well let's open this bad boy. Okay, world file, remote report file, that's fine. Extra include deers? No. Extra lib deers? How about nothing for a start? Extra proc path? No thank you. Install deer? Sure, why not? Build log, okay. Jobs, sure. All this commented out. That's fine with me. We save and we try again. Cabal, build, and let's start with CUDA. We could actually, and I shall do that, remove this guy, because now we know some of the root cause for this. And I'm going to make a note of this in the log as well. Maybe in the, not this one. Kind of gotchas. I installed a Haskell platform. And installing it didn't clean up the Cabal user config, which was located in this place. Okay. configuration changed. It's also revealing a bunch of stuff that maybe it thought was located in these weird places. Oh, that's good. I'm glad we get rid of that. Okay, maybe you remember this issue. How about we drop a note? It wasn't closest to this one, it was closest to this one. Except it's closed and archived, so we can't answer on that one. I suppose except if we link to it again from this guy. MC is passing correctly recognizes relative on Windows. That's not the error, right? But pass not handled properly. Try. Brew install? What is it supposed to be on OS X for Windows 10? Why not on Windows? No using a path with spaces. So why do you jump on this issue then? It's going to be hard to find the proper. So yeah. C program file doesn't exist as in a directory. I suppose I could check out Stack Overflow. Go back on fig file. Maybe it's a known thing. Well, it will be in my blog, so hopefully people will find it that way. And yeah, I should add the error messages. Right, yeah, let's copy this for laughs. This is really the weirdest possible thing, right? Oh, I suppose this is the pretty printer kicking in or something. I don't know why these things are like this. This is so strange. And right, so I think this is basically going to be the keyword and the error message during the build was included in the, what is it, CUDA.buildinfo, a generated file. These mangled path were also included in the, Okay. Hopefully this will help future users. And how are we doing with build? We seem to be rebuilding a bit of low-level tooling here. Right, and we will need to actually add the proper path for the libraries we care about, but that we can add as the in the actual shell path, which I think we already did, right? Maybe not in this particular environment since we restarted it. So we might have some of these DLL not being found, but we know how to deal with that. So let's let it build, and I'm going to take a small break and be back in about 5 minutes. And I'm back. And we seem to be building. We seem to have generated a new build info file, and I seem to have misspelled path. So let's go check out our build info file, and it looks nice and clean this time. And it has picked up the path for at least the basic CUDA library, if not NVVM, but that's probably okay for now. Let's see whether it yeah, no, this needs to be in the path, so that's all good. We can absolutely do that. We just need to go back and yeah, go back in time a bit here and pick up those two paths we are going to want, these two guys, and write this down into our instructions. Yeah, that's basically it. Okay, go for it. Okay, so let's check where this library is supposed to be. Is it one of these that's supposed to be here? 2.64. No. So yeah, maybe it's not in the bin. Not in the bin folder. If not, then where was it? What else did we add there? Not much that was directly that was related to CUDA. So let's. Could it be that well, let's check that path. Yeah, it is here. So how about I do the user config update and see what that does. Do we still have it somewhere? Open editors, right? It is not here. So what did this do? Exoproc path, symlinks, installed here. Nothing special, huh? Program locations and whatnot. So I thought this would be solved by path, but visibly not. Dependency not loaded. I mean, mind you, we're trying to build NVIDIA device query here. And I think specifically when we tried this instead of doing cabal install CUDA, with the cabal run, then we did run into the same issue. Which led me into this goose chase, this wild goose chase, thinking that maybe it was a 64 or 32-bit binary compatibility issue. So let's revert to trying to build our actual project of interest and see whether we're bumping into the same problem. Yeah, just to show you, this is exactly that error we had, and that's when we try to do cabal run NVIDIA device query, and didn't work even with the correct DLL in the path, but if we did cabal install, then we were able to run NVIDIA device query. So don't want to pay too much attention to that. And oh boy, I think we're going to rebuild everything because the cabal user config changed. So that's going to take forever. And there's nothing we can do about it. So let's. So that's our license to take a look at more Accelerate. And maybe we want even to start something fairly ambitious, which is to go into the Accelerate examples, except it's not going to let us, is it? Examples, NBody. It could be that if I maybe opened up just this path, it might work. Oh, visualizer. I didn't even realize that there was a visualizer in there. What is this? Ah. Okay, that's the original example. Huh. Interesting. So interesting that they commit that inside the, I guess, some kind of tip of the hat. Oh, there's a visualized as HS though, which does what? Okay, so there's something I haven't understood then. Running the NBody simulator. Run the code from inside Visual Studio or go to the bin Win32 release directory and type NBody. But I think this doesn't say anything about Haskell, does it? No. So I think this is just a copy paste of the code from. It's probably we have it in probably similar shape inside the SDK, but I think we're just going to bypass that, right? Yeah, with the gem. Okay, so our main interest is going to be in trying to build some kind of credible Barnes hut code without having a real programming environment quite yet. But I suppose that's fine. What's in config? Okay, the 3 solvers. And so yeah, when we do Barnes hut, then it goes to Barnes hut doc. So it's already pretty much set up to run, except right now it's just going to output that error. So how about we start with one of the two examples? Which one is it going to be closest to? Let's look at the, yeah, this guy. Constructing the Barnes hut tree. Crucial idea. Is there a more linear description? That's the one. I think we probably are not going to find something much better than this description. So let's get reacquainted. Speeding up the brute force NBodies to group nearby bodies, approximate them as a single body. Yes. Far away can approximate gravitational effect. Yes. Formally, two bodies have position x1 and masses, then the total mass center of mass. Barnes hut is a clever scheme for grouping together bodies that are sufficiently nearby. It recursively divides a set of bodies into groups by storing them in a quad tree. Quad tree is similar to a binary tree. Wonder what the difference between a quad tree. Also, the arc tree must be in 3 dimensions. Quad tree must be for 2 dimensions. Quad tree is similar to a binary tree, except that each node has 4 children, some of which may be empty. Each node represents a region of the 2-dimensional space. Yeah. Topmost node represents the whole space. So we know that. That's fine. Each external node. Check out my previous streams for more detailed run through of this, but we're going to get into the programming of it, so should be also explanatory. But if you're joining this live, feel free to ask, and I can run through it again. Each external node represents a single body. Here's an example with 8 bodies. So that are 8. Calculate the net force. Okay. To construct the Barnes hut trees, insert the body one after another. So insert a body B into the tree rooted at node X. Use the following recursive procedure. If node X does not contain a body, put the new body B here. Okay, I'm already confused because if we're inserting, so we start into the tree rooted at node X, so we are at this node. If node X doesn't contain a body, it doesn't, right? So now we have a body, so we put it there. Okay. So then we have a single body A at the root. Now I guess now we want to put B in, so then we check out node. What do? We start again with node X. This time it does contain the body. It's an external node containing a body C. Then there are 2 bodies B and C in the same region. So we subdivide the region further by creating 4 children, and then recursively insert both B and C into the appropriate quadrants. Since B and C may still end up in the same quadrant, there may be several subdivisions during a single insertion. Okay. I think that makes sense, except the... Oh, yeah, no, it makes complete sense. Okay. So so these maps a move onto the bodies, and I suppose we are going to need to do this in 2 steps. We're going to first do something like build tree. Are we gonna, is that gonna be a map though? It's not, right? It's going to be a fold. Which, okay, which this build tree is already. So let, well, so it's just build tree. That so it's just tree really. It's just really tree, I believe. And then we'll do something with the tree, but for now we are not preoccupied with it. And so we fold something. I mean, I don't know if a fold is actually, well, yeah, no, fold might work. But we don't start with 0 for sure. We start with some empty tree. And so we need some octree. You know what? I'm going to look at what the data parallel Haskell folks have done for that particular representation here, and I think that was a smart move. The size of the cell, centroid, XY, mass, and the children. Sure. Tree, double, well, except it's not going to be double for us. It's going to be something different. Oh, tree? Okay, I see. Okay, well, fine. Fine. You have prepared everything, and so I shall do this in the proper place. And let's look at our types. We seem to be using floats because not all compute devices support double precision, I suppose. And type is R, velocity is R, position is R. So I suppose we need to call this R, or R like real, yeah. Yeah, well, actually, we have an actual type for this. So we are going to need to import size of the cell is not a position. Centroid X and Y is, and mass is a mass. And so if we want to have some kind of dimensions, then I suppose the size, that's an interesting thing though. This is the 2D, this is the 2D algorithm. Yeah, it is the 2D algorithm. So size, so do they mean area here? Is that what they ended up doing? There's a bounding box. Oh yeah, well, so it means that, I mean, bounding box, it must be given to us as a parameter, right? Yeah, that's the box, so then the question is, what do you do with size? And is it LLY minus LX times LUY? Yeah, okay, well, that's the build tree. But BB prime. PHT S, where S is either S6 or SY. I see. If SX is smaller than SY, then it's SX. So it's the smallest dimension. I'm not sure why how they use this size. Let's check again. S. Well, it's not in use during the building of the tree. I mean, that I can see. FTP, subtree, boxes. Yeah, I don't see LS being used in the actual construction of the tree. It goes in that, but it must be used in some other fashion. And that's the recursion. Split points is what assign mass points according to the location in the quadrant. But this, okay, well, no, this does contribute to the BB prime, but that's the bounding box. So we split the bounding box. It still doesn't, still don't see where S is used at this point. Calc Haskell, text S is far. Oh yes, of course, it's the width. Yeah, it's that part of the algorithm which is used to determine the precision. Determine the precision with S over D, and S being the size of the cell and D being the distance to the node. And if that's greater than some preset constant, then you continue. But if you reach and you're inferior to some theta, then you stop and you consider that now you have a internal node or a branch node, an intermediary node that can be that is an okay enough representant for all of its children node, and so you that's how you shave off a from the n squared to the log n. Okay, so that's why S is stored. And this way you don't have to recalculate it each time. Okay, yeah, I'll buy that. So in that case, I think it being just an R, I think is fine. We can say we can give it a, we can follow the lead here and say size equal R. Maybe even type. Right, these are types and names. Yeah. Okay. And so yeah, so then this becomes size, position, mass, and a tree. Okay, let's see how our compilation is going. Oh, well, it's still going. And so so we now have some kind of data structure. So if we go back to our bounce hut, then this is sort of our build tree function, really, right? I mean, if we can, I mean, maybe the fold can be the build tree. Yeah, I think that makes sense here. Like we say, build tree will be where we pass to the fold, and build tree equals this for start. You know, just picking up on the naive version, except the type of this now is going to be, we're going to start with a tree of size. Well, size is going to be the size of the world we're considering. So where do we get that from? Window size. Window size is the size of the window into which the world is projected. Doesn't give us the size of the world. We do have a universe, which is initialized world. And so is that here? No, we didn't config. Default. Options, no. And yeah, size is the visualization size. Also, 1000 is what, 1000 times 1000? Maybe. Start with 1000 bodies. And a body mass of what, 1.6 kilogram, or maybe 1600 kilograms, maybe tons, maybe more. So not clear where initialize comes from at this point. So let's try and find out. From simulate. From gloss simulate, I see. You'll just put the world in simulate world and draw tree, huh? Oh, I see. That sounds like maybe that's related to that super neat visualization we saw, where it seems like the tree was displayed here. Yeah. But it's not used now. Okay, and but then we pass it world, which comes from where? Just from here, and world is just some bodies, and we don't have a size of the universe. So I suppose we need to calculate it initially from the random array of positions. Oh, actually, random array of position is created from a, I mean, we need to look up random array, but it's created from this cloud. We need to also look up cloud of size. So size is going to be 1000 times 1000, and so it seems like a reasonable thing to use as the initial size. And so this S in 3D, is it going to be in fact an area rather than a distance? Let's see if this says anything about 3D in here. No. So let's look at a more sufficiently far away. S is the width of the region represented by the internal node. well, yeah, angular width or something, spherical angle, or I mean, we're fine approximating it, I think, with either a distance or an area. What do I think here? I mean, this is an approximation algorithm. So if we save, it seems like we can save a bit of computation by just making it a distance. And so the disadvantage of that is that we'll need to choose an axis, and so there'll be a bias. So let's do it properly. I think it needs to be an area, not a distance. So it would be we call it an area. How are we going to compute that? Well, oh, I see my. No, we can. Yeah, we can consider that it's an area, but we actually don't need to compute anything specific per quadrant because we will make each quadrant a cube. Meaning that we have a bounding box at the get-go that even if our initial point distribution is skewed or more parallelepipedic than cubic or rectangular than cubical, then we start with an encompassing cube. And so we'll have some empty areas, but because this is a algorithm that's in fact designed to deal with sparsity well, we don't care. So we can make it width. In fact, this will be one dimension of the bounding octant, something like that. Okay. And so, as I said, we start with the largest possible, and so that would be size times size. So we just need to pass this to our calc Excel somehow. So maybe, well, we do pass equal epsilon bodies. Hold on, is that right? Yeah, no, it's not right. Yeah. And so we also pass, oh, then. These guys all have the same interface, so we're going to need to update all three and just ignore the size at the get-go. But unless we shift the calculation outwards, but yeah, no, that doesn't make sense. Solver, constant epsilon, and so on. So yeah, so let's pass size to the solver and change the types. And ignore size here. And ignore size here as well. And we need to check whether we actually pass an XPR, if size really is an XPR. And then it's going to be a tree size something, something, something. center of mass would be 0. I mean, everything would be 0. And the mass would be the total mass of all the bodies. And so we want to calculate that. Total mass. So we do need to do a pass to calculate that. We do have the bodies, and it will be something like a sum of... or probably can do this in parallel, in fact. And we'll find out how to do that somewhere. Probably around here, mass of point mass is a second. Taking the point mass. Yeah, but so let me check what. Yeah, body. Okay, so first of point mass. So it's the combination of first and second, but we can probably just reuse point mass of body. Well, point mass of body composed with its mass of point mass. I don't think there's a shortcut right there. Not that I can see. So those really are lenses, but I think maybe this example was built before lenses were in. So we do need to import this from common bodies, I believe, or common body. Body. And, well, point mass of body and mass of point mass. And well, we need to know what the accelerate sum is like, and we're still building over there. So let's go check out accelerate. And I suppose that's going to be here. Sum, prefix sums, elements, sum, that's some type, that's something else. Oh, I think we went past. Okay, yes, that's some type again. From list, FFI. Float. Expression language. Prelude, that's... Really, you mean prelude here? Oh, sums, scan, segmented scan, prefix sums. I don't think that that's what we're after. Maybe he is folding, so... Oh yeah, fold of plus. Oh. I suppose that's the way, but we also need to map So it's really something like a fold of plus of something like mapping mass of point mass dot point mass of body to bodies, something like that. And the empty. Oh, right. Hold on, that's not right. The type is not right. It's not just one tree we have here. We actually have 8 children trees. So I suppose. Wow, that's funny. I suppose we will have to do it like this, right? There's no. I mean. One, two, three, 4, and 1, 2, 3, 4, right? Those are 8 children trees. Oh, but we need to distinguish internal nodes from external nodes. Which is to say that we need to have another constructor, I think. Yeah, right. We need another constructor for leaf nodes, or which are called external nodes. So let's call them leaf. And a leaf is the same, but without children. So that's kind of like what I was calling a branch, right? Okay, yeah. It's a little bit strange to stack them 4 by 4. Let's stack them. Let's stack the 8 of them. Okay. And so in fact we start with a leaf, and so it might not be the more computationally efficient to start with a leaf and do what's suggested in the example, which is convert it to a branch, because it says if you've got 2 things in the same region, then you subdivide the region by creating 4 children. And for us it means, I suppose, converting the leaf into a branch. Maybe I'm overthinking this at this point. I think there might be a better way to do it, but let's keep it simple. Maybe this is naive Barnes hut. By the way, it's not Barnes hut like this, it's Barnes hut with an E. So let's also correct this. And I think that's it. And how's our build? It's building. Okay, so what were we saying? We're saying, yeah, we got some, suppose, total mass. Yeah, we're saying that we start with a leaf. That's what we were saying. And then this constant z, I think, is the shape of the fold, and so it just means that I think it just means we're folding across well, the only dimension of bodies, since this is a vector. So our accumulator is our tree, right? So let's call it, well, okay, fine. Let's call it accumulator. And what are we going to do with it? It depends on where we have next and then what's on the tree, right? So first time around. So yeah, what about the notion of contain a body? Oh, I suppose we use size for this, right? We say 0 and size, half of the size in one direction and half of the size in the other. If you contain inside that, then you so let's think about it. In there'll be some case which I'm not sure what it would be, but we know that there's what? Oh, is it 3 cases? Yeah, it is 3 cases. So there'll be the case where X does not contain a body. Yeah, this whole acceleration thing will be down there when we do, after we've built the tree, then we will map, we'll do the similar map than what we picked up here. It won't be move, it'll be calc or something. Such that we'll somehow map this calc function over our tree, I believe. Well, over our tree and our bodies. So I think that's what it will mean here. But I suppose we could write it like that. Yeah. But that's for later. And it will be, yeah, there will be some other smart things there. So when we say that in the case where we just put the new body be here, what does this mean? It kind of means, oh, well, right. Huh. So maybe we don't need the total mass. Maybe we start with 0. Yeah, we do, of course. So that wasn't needed. And so putting the body there means we now have, oh, we do need to, do we need to hold to the body? No, we don't need to hold to the body, do we? Oh, I think we do. Huh. So hold on, let's look at the DPH algorithm again. Especially the data type. It has a centroid. Oh, they actually use a data parallel. Oh, because they do nested data parallelism here. Ha ha ha. Fancy. But they don't actually store, or is it the case that if so, then you just say leaf and then, well, size I don't know, but you actually take like, well, next is a body, right? So don't we want to do something like P, what is it? PMVA. Well, we only need PM, right? And PM is position mass. So, oh yeah, I'm missing a dimension in my tree right there. I need another position unless I reuse the type. Unless no, it's just one position. What am I saying? Yeah. It is just one position. Yes, yes. Oh, so we could have a point mass here instead. Sure, why not? That's what it's made for. And so here we have our point mass, and it's a position, which is itself. Oh, this is so ugly. We can use a pattern, view patterns here, though, right? So we could do something like point mass of body. Is that how it works? Still building? Still building. Have we built anything impressive yet? Like CUDA? No. Not at all. Not even close. Oh. Oh, hey, we linked NVVM. That's pretty good. Huh. Okay. I'm pretty happy with that. And what time is it? Hey, 15 minutes past my time. Okay, I'll take a little break. Wow, it's installing things and whatnot. I'll take a little break, and yeah, we'll see how far compilation goes, and whether I have 15 more minutes in me to carry on with this. See you in a bit. And I'm back. Yeah, let's go for another 15 minutes. Things are still building, and there's like the drums are rolling. Are we going to make it? Is this going to build? The end, at the very tail end of the 10th stream. Yeah, we shall see. Okay. So I was wondering, maybe we don't need to actually go on the bodies here, and we could do that trick that we wanted to do here, which is to, and so I don't know, this will relate to how optimizations work, and I'm not super familiar with that, but I suppose here we're giving it some layout indication. Oh, wow, I'm getting distracted by the fact that things are compiling. Ooh, exciting stuff. I don't remember whether we went as far as accelerated LVM PTX. I think we probably did, but if this compiles, this is dependent on both LLVM and CUDA to be properly linkable. So that'll be awesome step. Okay, yeah. So if we map, so I don't know how optimizations are going to work here. There's two possibilities, right? One is if we reuse the same bodies layout, but that we pass it different shapes, then it would be able to sort of optimize that. The other idea would be, no, it needs to create like some kind of secondary tighter array, and then it will build on that. I don't know. Let's try with this. It will simplify a little bit the code here, because we can say something like XYZ. No, actually, we don't even need to say that. We can say PM. Actually, we don't even need to say that. We can say point mass, and we can pass the point mass to the leaf, because now leaves only have width and a point mass, if I'm not mistaken. Yeah, they do. And let's copy that, because I'm going to be switching back and forth otherwise. And we'll want to import, oh, is that going to be, that's going to be a circular import, isn't it? So I need to import commentary in to get our I suppose if I do this, then I can only import commentary and it will be fine, I think. Okay, I want to see this. This is the last step of LLVM PTX build, and I don't remember whether we went further than that or not. Hello, Mistron. Oh, to be honest, I don't know how big this is going to go. In this naive implementation, the default config was 1,000 bodies here. But I was looking at, what was I looking at? Oh yeah, so some of the more recent papers for nested data parallelism, and they talk about quicksort, but they talk about quicksort with numbers that didn't seem very big. But I think quicksort apparently would be applicable to creating the octree for the Barnes-Hall algorithm. So I don't know these days. What is a good number? What's your experience with it? I was thinking like 10,000 should be okay. I don't have like a supermassive GPU, but it's fairly recent. It's Titan XP 2080 NVIDIA CPU GPU. Yeah. Yeah, you know, I'm looking forward to doing like pretty visualization, like galaxy style things, right? I don't. This one is the 2D, and it's also using Haskell, but it's from 2012. It uses a different way to do GPU accelerated high performance computation. I'm going to be using this accelerate package from that's sort of the current way to do accelerated array processing, both on CPU and GPU, and we're going to be using the GPU backend. And yeah, I'm really curious to see how far we will be able to go. You know, at some point I will compare with the native NBody program that comes with the NVIDIA SDK. I haven't ran that one on stream yet. I ran it, you know, for myself, and I was seduced by it, and I wanted to do it in Haskell. Have you ran the NVIDIA SDK NBody project? It's really neat, and I think it goes higher than 1,000. I'm pretty sure. It looked pretty. It looked like more, maybe 10,000, and it ran really smoothly at 60 FPS, and it was really pretty. I want to see how far I can get with Haskell. And we're still at our 46th step of compilation here. So let's continue. So yeah, our leaf has width, a position. Oh, right, so it doesn't need the position now because point mass has the position. So let's remove that. And so size, what is going to be size then? Oh, it's a V3. Yeah, I forgot how to build those. I will look it up. And mass should be 0. Oh, well, actually there isn't a size for a leaf. Oh, yeah. Right. So are you familiar with the Barnsat approximation? Because I think it is similar to what you're calling far fields, which is that it separates the world in quadrants or octants in 3D, such that for clusters that are fairly far from a given body, then you can approximate the cluster to being one single body, but with the accumulated mass, and that shaves off some of the complexity in the algorithm to make it run faster. So that sounds like what you're saying with far fields. Yeah, exactly. Yeah, it's the first time I implement this, but I did go through it last stream, I think, and it kind of makes sense. I think I'm getting it. So, right. So we were actually looking at the steps. Right, so if there's a recursive algorithm there that I was looking at an basic implementation of while we're going through the pains of trying to build this library on Windows, which is not my platform of preference, but the platform on which I've been streaming so far. So I've been a little bit stubborn and trying to build that whole stack on Windows. Also because it seems like very few people have done it or documented it, and so I feel like giving back a bit by documenting it, but it's been a bit painful, I gotta say. Okay, so if not X is an internal node, update the center of mass and total mass of X, recursively insert the body B in the appropriate quadrant. Right, so that means that we are pattern matching on our accumulator, aren't we? And if our accumulator is empty, so if our accumulator is a leaf, and leaves don't have size. So no, basically it means that we start with whatever the first body is in our tree, right? So maybe we just start with like a vector 3 of 0, 0, 0, and then whatever is the content of the leaf, we replace it by the proper leaf, and that takes care of the case of a single body. Trees are not very GPU friendly though. Exactly. So that's really what gets me to these more advanced techniques that are nested data parallelism. And in this thesis, and that's because I like to. It's easier for me to think about these things in Haskell, because otherwise things get a bit unruly. And I've watched a few talks about nested data parallelism, and that specifically, I think, comes down to what you're saying, is that, with nicely stacked arrays, everything is good and GPUs can be really efficient. But as soon as you have some kind of recursivity, for instance, that's going to make different branches grow at different paces, and the classic example is actually quicksort, where you subdivide your array, and you can end up with sides that are unbalanced, and so they will end up computing not the same amounts. And so you don't have a regular structure to go through. Your structure might be biased in one way, or you might actually discover your structure as you go. Right. Yeah, exactly. You want to avoid indirection as much as you can, and you want to properly parallelize your workloads onto your GPU cores. And so that problem is a hard problem. It's not really solved per se. There's a specialized compiler for that. Nested data parallelism, the Futhark language, and that is mostly related to what's called regular nested data parallelism, which is a subset of data parallelism, but I think which includes specifically algorithm like quicksort. And algorithm like quicksort are in fact a special case of the type of octree that we're building with the Barnes-Hut approximation for and the NBody problem. So it should be possible to apply the type of work that is done to compile nested data parallelism code of the quicksort type. And so trying to make the Barnes-Hut approximation look a bit like quicksort, because it's apparently I picked up in a Reddit post that it's supposed to somehow be the same or similar. Right. A very fast way to construct a tree is to use quicksort-like partition. And when I saw that, I clicked in my head and I thought, oh, wow, actually, nested data parallelism is supposed to make quicksort fast. So unfortunately, though, apparently the construction of the tree is not the most data or compute intensive task in the Barnes-Hat algorithm. But I think I need to implement it to sort of get a better handle on that and see whether, in fact, some of the advances, specifically around nested data parallelism, this time not with this dedicated language and dedicated compiler, but with, in fact, a fork of the library I'm using, a fork of Accelerate in Haskell. That's right here. It's the feature sequences fork. And that implements exactly this same subset of nested data parallelism, meaning regular nested data parallelism that Futark is implementing. And so I'm thinking there's a possibility to reuse that to at least make the tree construction of the Barnes-Hat algorithm go fast. But who knows, maybe also make the other part go fast. And since this is my first foray into any array programming languages or GPU programming in any case, apart from basic using of libraries for 3D rendering or stuff like that, then this is all fairly new, but this sounds quite interesting as a possibility. So that's why I'm looking at all this. And also, hey, we're still stuck on the 46 task, but I think my GHC is still computing. I can see it in my task manager, so that's good. Okay. Hey, Mistran, can I ask you, were you just browsing on Twitch for programming streams, or did you come to the stream through some other pathway? That's cool. That's cool. Yeah, it's hard to it's hard to optimize for the good signal to noise. There's been plenty of time where I've been pedaling, feeling like I'm not moving forward, which often happens, right, when you program. But doing it on stream is a little bit painful for viewers, I think, and there's no immediately good solution for that. But yeah, I've decided to stream a little bit less, so maybe that I'm a little bit more fresh when I do stream. That's nice. That's nice. What's your well, I guess area of choice when you go to hard problems? Right. Yeah, I think so too. I've learned a lot by watching, some of the people that I consider my masters, that are, hearing them thinking, and specifically around Haskell. That really motivated me to learn more and to stream myself, I gotta say. Have you tried streaming? Branch. All right, so R does not contain a body, I suppose, is having a 0-point mass. So, all right. Yeah, that's how I started. I've been like for a year, I've been thinking about streaming programming, but I couldn't, decide myself to do it. I, always thoughts in my head like, you're not good enough, you're not going to be able to pull it off. And then, yes, right. yeah, and for me, it was a mix of things. Like this Mars colonization Paraspera game came up, and I was like, oh wow, this is an awesome game. And then I was like, oh, hold on, let's stream it. How about that? And then I started streaming the game, and then after a week or so, or 10 days after I finished it, I was like, okay, fine, I'll try and stream programming. And yeah, I do have a desktop setup, and it makes it easier. That's nice. That's nice. Yeah. Do you have like one of these little stands that you can put your body beneath of? I wonder if I'm going to need to actually make a difference between these two here. Oh, do you rest your laptop on your lap, or do you have one of these contraptions, like a small table that you can, put on top of you, and put your laptop on, and your other stuff? Mm. Ooh, yeah. Oh, on your lap. That's cool. What you're using C++ for that? Compilers, yeah, that's when things start getting interesting, right? In terms of challenge. Okay, node X is internal node, update is center of mass and total mass. Yeah, that makes sense. Hey, I would be remiss if I didn't pitch a little bit of didn't do a little bit of Haskell evangelism. You know that this state of the Haskell ecosystem post or page on GitHub that shows what Haskell is good at, and the thing that it's best in class for is compilers. And so Haskell is an amazing language for writing your own compiler. Admittedly, I haven't heard about JIT compilers actually built in Haskell so much, but it's one of these things where there's lots of tooling, and there's a lot. In fact, that Futak language, that's actually written in Haskell. Okay, you do know it. I won't. That was it. I'm not going to be heavy about it. Okay. If X is so in my data type for now, I only have leaves, which are, I guess, internal nodes, but I don't have empty internal nodes. But I don't think I need empty internal nodes. But you know what? Maybe I do. Let's create an empty internal node, because now I'm thinking, what am I going to put inside those things? And clearly, it's going to need to be empty internal nodes. So let's create an empty. Oh, wow. Nice. Very nice. Miranda is it's the ancestor of Haskell, right? And didn't they, am I confusing my programming language history here? Didn't they open source the code like really fairly recently? Right. Yeah, they did. Miranda released as free software 11 months ago. Yeah. Yeah, finally. You know that the reason why. Yeah. But I think that one of the reasons why the whole Haskell clique from the beginning decided to build the language, one of the reasons why that Miranda didn't want to open source at that point. Otherwise, they would have gone for Miranda. But the fact that there was no open source research language that everybody could use to implement their algorithms and in a way that was reproducible, then they just ended up creating Haskell. But just recently, like just less than a year ago, it was open source. Pretty crazy stuff. That's nice. That's nice. Yeah, I'm fairly recently started to pay interest to the more computer science side of computer engineering um, by learning Haskell, to be honest, because there's so much inspiration constantly streaming in from the computer science world that I started paying attention. Yeah, that makes sense. That makes sense. It's funny, I heard that one of the guys that I follow quite a bit, that's a really good Haskell programmer, and that also is trying to popularize category theory for programmers, called Bartosz Milewski. He comes from the C++ world and was doing concurrent systems in C++. But also, I heard him say in an interview recently that one of the things that led him to Haskell is the fact that templates in C++ and have restrictions that are in fact quite similar to functional programming languages, and that there was a lot of idioms streaming in from the functional programming world into the template language in C++ because of the similar restriction of like compile time, and I think immutability and pure functions. No, I've never used them, but that was a piece of trivia. I guess I didn't know that some developers actually discover functional programming through that path from C++. Okay, so now we have an empty node, so we can do things a little bit more cleanly. We can say, if we match on empty, then we return a leaf. If we already have a leaf, then what do? Yeah, I think it's gotten much better. I remember I looked at it, more than 20 years ago, and yeah, it wasn't pretty. And also, I think I wasn't maybe ready for it. But yeah, it seems like it's gotten nice. I'll probably take a look at it at some point. Right. Yeah. I tend to be a little bit of the fanboy here, and I think I mean, let's say I'm still discovering so much in this space of functional programming languages that yeah, I'm not necessarily, I don't feel the pressure to learn anything else for now. But the part that's the most interesting to me is sort of this these higher order abstractions and how that guides the thinking about large amounts of codes, and that's something that is still inspiring for me to continue learning. Right. Yeah, and allowed some things to be a little bit more terse as well, right? The terseness of the code of Haskell to me is such an enjoyable thing. I guess because I have a minimalistic aesthetics, but it's just like I can't look at code with so many what looks like so much ceremony around it. That's nice. That's nice to hear. Yeah, I mean, right? Like you can do small things like this without having to lose your flow too much because you're going somewhere else and writing a function signature. Yeah. Okay, so if we have a leaf, we update the center of mass and total mass of x. Right. No. So right. So this is actually an internal, what's called an internal node. And this is an external node. So with an internal node, we update the center of mass and total mass of X, right? So so this this is impossible. I can't do this really. Then I probably have to build an intermediary data type because we're doing octants. So each branch of the tree has 8 children, but it feels so weird to have to write them all there. Oh boy. But maybe I have to. Okay, so this is the width, and this is the point mass, and then those are the 8 unruly children. And which one do I do first? I want to do the external node first, actually, because I think this is more complicated but interesting too. Say containing a body named C. And there are 2 bodies B and C in the same region. Subdivide the region further by creating 4 children. Or it's right. So it means that in the end we will return a branch. And yeah, well, it will be made of 8 empty children. And so here I'm starting to feel a little bit the pain of this. I mean, I suppose I could create like a V8 of tree or something, and then well, for now, let's just do the crazy looking thing. So I create a external node with these 8 empty children, but that's not where the interesting bit happened. Recursively insert both B and C into the appropriate quadrants. Right, so in fact, indeed, I will need to... So the way that this was done in DPH is they had a specific function for that, right? So it would be like an assign function. But here we're creating a new tree. So I suppose we could create it with width 0 and point mass v3 0 0 0, and we could call this an empty branch. And then we could say that we are assigning, right, because we have an existing point mass in the leaf, which we can call PM prime in Haskell tradition, and with an existing width, right? And so we're going to need to divide the we're going to need to divide the width by, and where am I calling it? S, I'm going to call it W, and we're going to need to divide it by 8, because that's what happens to an octant divided into 8 new octants. And so, okay, maybe we'll call it then new branch and say that it takes the width, and then we'll say that we need to assign both PM and PM prime. So I suppose we could have could make a list of those to a new branch of W divided by 8. Hey, Mr. Ron, think about Haskell compared to earlier functional programming languages, probably the monads between imperative and functional work quite regularly. Yeah, absolutely, absolutely. Completely agree with that. Part of the also it's really interesting, right? Because it's also what in some sense, maybe it existed among the computer scientists that were part of the early Haskell community, but it seems like it's the first sort of the way in which category theory kind of showed up inside the Haskell world in some sense. That was one of the strong exports from category theory that turned out to be a really elegant practical implication to do side effects and I/O. And yeah, really fascinating stuff. Do you use monads much in C++? Oh, how's our compilation going, by the way? Still going. JC is still going brr. Okay. So now we have some assign function to write. And I think we can make it a proper top-level function. That makes sense. Applicative order languages, though, is something that I haven't heard before as a term. Huh. So applicative order is also strict. Yeah, that's great. I'm really happy to learn about this. Also because, you know, does it is it the same as the applicative, you know, in the functor, applicative, and monad hierarchy? It's not, right? It's just an overloaded thing. Let's see. There's probably some images for that. Yeah. You know about this hierarchy, right? Functor, applicative, monad. And since we were talking about monad and you say applicative order, I'm like, applicative? But I think it might be a different term. The function's argument are evaluated before the function is applied. Oh, yeah, okay. So yeah, makes sense. Oh, so normal order is the same as lazy? Okay. Huh. Oh, here it seems to be distinguished. I don't know. Lazy, while normal order evaluation may result in doing extra work by requiring function argument to be evaluated more than once, applicative order evaluation may result in frequent. In practice, most functional programming languages solve this problem by using lazy evaluation. Oh, I see. Wow. So that's a pretty subtle difference. Is that that normal order leads to doing lazy evaluation in order to not do too much work. Thus combining the effects of normal order and applicative order evaluation. Interesting. Yeah, that makes sense. Cool. Today I learned about applicative order and about pretty uninteresting things about building Haskell libraries on Windows, but also a little bit more about actually implementing the button sort algorithm. Right, so assign will be, so what I'm saying now is that, well, we kind of want it to be a vector of point mass, in fact, right? And so I'm probably not going to want to build it like that, that's for sure. There must be a constructor for this. Interesting, because I think what you're saying seems to me to fit with the idea of memorization, but I'm not sure that lazy necessarily means memorization. I think we evaluate when needed, and after evaluation, all copies of that expression are updated. Right, so, interesting. I wonder, so maybe it is, oh, right, that's linked to sharing, I think. Yeah, I think in practice you must be right. And I think usually this is called sharing, right? You know, immutable data structures. Once part of your data structure has been computed, then everywhere else that it's referenced, it's pointing to the same thing. So it makes immutability practical, right? Because you don't have to actually copy all your data structures to not modify the previous one. Yeah, cool. Very cool. Yes, indeed. That I knew. So I think then we are returning. Oh, well, one of the weaknesses of this is not at all in the accelerate monad. So that would need to be changed. Oh, and maybe then we could make this into a shape. Actually, we might need to make this into a shape in order for any of these nested data parallelism thing to occur. Yeah, absolutely. Absolutely. Well, in fact, it does at the end of the world, right? And the compiler and the runtime do this for the programmer, so that the programmer can stay in pure land all the time, and have those mathematical guarantees. Yeah. That's right. Have you heard about free monads? That's something that's been quite propped up in recent time. It's a little bit connected to this idea of extensible effects in Haskell and in other purely functional programming languages. It's this idea that, you know, I/O and the I/O monad is great, but it's not granular enough, because it's basically, you know, all possible effects are described there, and so it's a way to try and be more granular about the type of effects. So you might want to differentiate, you know, your network effects from your console effects to your graphics effects to your database effects, and then the difficulty becomes, how do you compose those things together? How do you make this useful and easy for the programmer's perspective? And then how, especially when you compose them, then, you know, issues arise around, like, okay, well, it might not be, they might not commute. Some of these effects might not commute. So you might not be able to, so the job, as you're saying, like the job of the implementer, the language implementer becomes a little bit more complicated because you have to take care of interleaving, of how effects are going to interleave and whether their order is going to actually create a different meaning. So that's pretty fun, but it's quite nice to write, and I think it's a natural continuation of this idea of monads that you're pointing out, that they're great for programmers and also great for implementers and also library implementers, because you can do a lot with that, and it's really fun. So is there a way that we can make this a vector? I think that's exactly when we encounter this nested data parallelism thing. And so if we want to be a little bit future-proof, we could start looking at this code in the sequence branch, and maybe compare it to the main branch so that we know, maybe see if there's some examples in there. State, this all looks like that's the underlying machinery. You know what? No, I think this was in another folder actually. I think this was pointed to by this quicksort. So what do things look like here for quicksort? We have a state type, which is just a pair of vectors. And a step, simply update this. This updates a single atom of state, it looks like. Yep, same for me. Absolutely the same for me. That's and it's not easy to even conceive of the fact that this is possible before you do it. But once for me, when I started learning, it was the first time I just bounced off it because I couldn't understand it. Yeah, that's very true. That's very true. But also there's a certain elegance and simplicity in some of the concepts that mean that once you've got a pattern in your mind's eye, then you really see it in a lot of places, and it really becomes useful. Like like a monoid, for instance, right? Or a monad, right? But the monoid is even simpler. It's just a thing that you can squash together, right, to create the same type of thing. And once you've got that down, then you see it everywhere, and it means that each time you see one, it comes with a number of already learned material in your head. So it's really teaches your mind to think about things in a much better way, in my view. Yeah, exactly. Map. Map reduce, right? Map and fold. I mean, just that concept of higher order functions. When you start getting that, and then getting a little bit comfortable with that, then you get map and fold pretty well, and then you get into recursion schemes, right? Like that. That's map reduce on steroids. With if people are afraid of the monad term, then with recursion schemes, you're like, oh my, because a fold is where are these? Oh well, recursion schemes. Yeah, reduce as well. Yeah, absolutely. Yeah, and this concept of so see, look, a fold or an unfold are a catamorphism or an anamorphism. And then you have helomorphisms, which are a combination of a catamorphism and an anamorphism. And then you have various other combination of these things that have like a zygomorphism and a paramorphism. Yeah, map is exactly the reason why you want regular things like arrays in your GPUs. Absolutely, that's the essence of it. And that's the essence of things like ECS, right, in game programming. Like an entity component system is in fact just a big map, right, with some nice inversion of control for components and stuff. But this whole data-oriented programming is really that. But yeah, map and reduce, in the way that you get the monad, and then there's like crazy, even more advanced category theoretical construct on top of it. Then you get the map reduce, and then like there's this whole reduction schemes on top of it, catamorphism, anamorphism, that are the higher order abstraction of fold and map. So it's pretty crazy stuff. Yeah, exactly. Yeah, exactly, right. And then the other idea is that the hardware is really good at dealing with regular data structure that's laid out all the same. Then it can parallelize, it can do branch prediction, it can feed its low-level cache really well, and then everything runs fast. And that is something that is hard to do in functional programming, where you don't have that much control over the runtime. But it's really interesting. Yeah, exactly. Yes, absolutely. Okay, let's see. How's this compilation going? It's still going. Okay. Well, but I am sort of fading now, and so I think I will look at wrapping up. And it's funny because I'd said that this is my 10th stream on this concept of trying to get this NBody simulation working in Haskell, but this is actually the first stream that I start writing some code in relation to that. I've been reading code from the Accelerate library in the past streams, and scratching my head, trying to, if not to say banging my head on the wall, trying to compile things on Windows. And I said at the end of the 10th stream, if I haven't succeeded in building this library on Windows, then I will switch to Ubuntu. But I think we might be there, but we won't know who at the end of the 10th stream. So that's a bit of a cliffhanger. But I suppose that at the 11th stream, I will be either on Ubuntu or we'll be back, and this will have completed successfully, and we will see pretty things on screen. But anyway, yeah, exactly right. Absolutely agree. The thinking part of computer engineering cannot be underestimated. And that requires some reading and some understanding. But hopefully, for me, I would have hoped that it would have required less battle with Windows. But that's really my own fault. I've been very stubborn in trying to make this compile on Windows. Yeah, I completely agree. And that's been quite new as well for me with functional programming. And seeing talented people do this, I think has been a good model also for me to, not see the reading part as wasted time, but indeed the moment where you're actually properly getting to grasp, properly putting in your mind the plan, and then you just have to roll out the plan, and it's much easier to flow in that way. And I've been feeling that a little bit as I was doing the beginning of implementing this. But I think there's still some concept that are missing for me here with Accelerate, so I'm going to need to read a bit more about it. But that will happen on the next stream. And just so you know, my streaming schedule is these days is I stream 3 times a week. I've been streaming like 6 times a week for the past 5 or 6 weeks, and I decided to slow down a bit and stream 3 times a week. And so on Tuesdays, I'll be doing continuing to work on this Haskell project. On the Thursday, I've been working on this PureScript prototype when I implement a real-time collaborative text editor on the basis of the chronofold data structure, which is a CRDT that's meant for that's optimized for collaborative text editing. And so that's another challenge because PureScript compiles down to JavaScript. So now I need to think about optimization with like several layers, and I'm quite interested at getting there. But right now we've been we've been playing with some experiments and with the UI library we've been using, and now the network, the distributed network library we've been using. Oh wow, nice. Yeah. I mean, that's awesome. Yeah, I've been, I think I've put my hands on a computer about the same time, and I've done some basic maybe then as well, and it was some time ago. But you're right. I agree with you that the interesting part is the problem solving, and so it's more about the mind than the fingers, I guess, or it's more about the meaning rather than the syntax. But I feel like there's definitely still some gaps in my theoretical understanding as well that I'm really looking forward to continue feeling partly with the stream. So thanks a lot for hanging out, my strand. It's been nice chatting and really nice to hear and learn about applicative order, execution, evaluation strategy, and chat about all this stuff. That's nice. That's good. Keep it up. I'm doing the same, and yeah, definitely send me a message if you end up programming on stream. I'll definitely stop by. And even if you play as well, I'll go check out your account and make sure I see when you come on stream. What have you been playing? Another 1cc. I don't think I know this. Oh, cool, these old school games. Nice. Yeah, definitely. Awesome. Sure thing. Well, stay tuned, and you're obviously very welcome back to the stream next Tuesday when we'll get back to it. And otherwise, yeah, if you're interested in the Haskell ecosystem, I'll probably push this as a PR onto the Accelerate example repo. Actually, maybe I'll accelerate examples. It will show up here because I'll show you specifically where it will show up, and you can watch the repo if you like, because they don't have a Barnsat implementation yet, and so that's the gap I'm trying to fill in this in these examples there. So if you watch that repo, then you'll see my PR at some point, and otherwise, feel free to drop by on the stream. Thanks a lot for watching. I've been Jun-chan, and I'll see you on Thursday for some PureScript, and bye-bye.